Our next lecture by Ekaterina Glinyanaya devoted to the point processes which arise in coalescing stochastic flows. Please, Katerina.
Okay, thank you. I will share my screen. Just a moment. So this is okay. So today I will show you the next lecture, and I want to recall that on the previous lecture we discussed that we want to describe the system of particles with interaction using method of theory of point processes. So we start to consider some characteristics of point processes, and today we will see how we can describe them. So I recall that we will consider a point process as a measure of the following form. So here we have some numbers of random points in space, and we just we consider a sum of delta measures in these points. And on the previous time, we considered one of the characteristics of a point processes, so-called intensity measure of it. So we learned something about this on the previous lecture. And in this lecture, we will see how we can characterize higher moments of point process, and to start understand how we can do this, we will consider example of a point process not on arbitrary space but on Z. So it is much more easy to understand the main idea here. So in this case, one can imagine that random measure we can consider, so we can put into the correspondence to a random measure a sequence that consists from zeros and ones. So now my point process is located on Z. So in each point I have or not have a random point. So we have here or not have, and so on. So random measure now is nothing else than sequence of zeros and ones. So now in order to define a point process, we need to define a distribution of such sequences in the space of all binary sequences. So we now want to understand how we can define probability distribution in this space. And it's not hard to see that we can define a probability distribution by defining their probabilities on cylindric sets of the following form. So here, if I define all such probabilities, where epsilon here 0 or 1, using this family of probability, I will define uniquely a distribution of a sequence, and so I will define a distribution of point process. And to do this, let us now come back to a point process. So as I said, we want to define such probabilities, but I can rewrite them in terms of a point process. So this probability, this random event I can write as a random event that I have a point in some specific x1 and so on xk. So if I have a sequence of epsilons, so I know that here we have a point, here we do not have a point, and so on. So here we do not have. So this means that I want to find the probability that at some points x1, for example, x2, there is one point in the point process. So now we come back to describing a point process using the family of such functions. So I will consider now the family of such functions that show us the probability that there exists a point in some fixed x1, x2, and so on xk. Here I forgot to write down the index of function f, because this function depends on k, of course. And I want to note that here this condition is important, because I will consider only non-equal points. Because if some points are equal, we will have the function with lower index. So here this is important, that if that each function fk defined on a set of non-equal points. So using this idea, we understand that we can define a distribution of a point process on Z just using the family, the consistent family of these functions fn. So okay, we built such a construction, and the question is how these functions can describe the moments of a point process, because I started from this question and I started to describe how I can define the distribution of a point process. So there very interesting connection between these functions, that they define so-called factorial moments of a point process. And before state the theorem, let me recall what is a factorial power of some number. So this is the definition. So I just consider the decreasing product of the following form. So here, note that we have we will apply this formula to value of a point process. So we will have this factorial power for a and n from a set of natural numbers. And the statement of the next theorem says that if I will sum all these functions fk, so I just want to recall that this is the probability that in these points xi1 and so on xik, that there is a point in my random measure. So I sum all such probabilities over all non-equal indices in my representation of a measure. So here, let me recall that I have measure mu of the following form. And I consider these points in some bounded subset B, just in order to have a finite value on the right hand side. So on the right hand side, we will get the expectation of factorial power of value of measure mu of subset B. So this is a very useful statement, and let us see the idea how we can prove it. So for the proof, let us start from k is equal to 2, and I will write this sum for two non-equal indices of functions xi1, xi2. So I recall that this function is nothing else but probability of the events that measure mu has a point at this position and a random point in this position. So here I can write this as expectation of sum over non-equal indices. Of course, here I miss this condition that all points considered from some subset B, and here I write just indicators equal to 1 and mu from xi2 is equal to 1. So now I can just consider this summation over non-equal indices, and here I will first consider summation with all indices without restriction. Mu from xi1 is equal to 1, multiplied by the same indicator, but here xi2 is equal to 1. And minus, I just need to subtract the diagonal, so this will be the sum where two indices are equal. So I will have just one indicator xi is equal to 1. Okay, so here in the first term we have nothing else but double sum, and I sum over all indices where we have some point. So this will be a value of measure mu of set B. So here everywhere I need to write that these points are in B. So here in squares, so I have two of them. And minus, this is just one sum, so here we have this. So this simple calculation show us just that we have second factorial power of mu of B. And next, the proof is the proof can be obtained by induction. So for assume that we know for k is known, And then for k plus 1, we just need to rewrite this sum over non-equal indices k not equal to ik plus 1 as I just split the last index over all. So I put here comma ik plus 1. Oh, I'm sorry. Oh, sorry. Oh, here. Here, and I should subtract here what is important. So I need to subtract all cases when ik plus first index is equal to sum of previous one here. So I will have k of them, and I not equal ik, and indicators. So I just omit because this is a very simple idea. So we will have from the induction we'll have mu k factorial power of b multiplied by mu of b minus k factorial power of b. So this is nothing else but k plus first factorial power of measure of set b. So here we saw that such probabilities that we define that can describe factorial moments of a point process. So this is idea that we easily understand on the case of a point process on Z, but this idea can be generalized to a point process on arbitrary space. And we will do a little bit opposite approach. So first, we define factorial measures of a point process. So let us start from such definition. So for arbitrary point measure, I can define factorial measures using this definition. So I sum such events when at non-equal points. Such non-equal points belongs to some bounding.
But nk is less than d.
Oh, I'm sorry. Here is the mistake. Here is d, of course. K. This is the same, and here k. Thank you. This index is the same. So k factorial moment and this k's factorial measure is a summation where we consider exactly k points. And from this definition, it is easy to see some properties of these measures. So I will not check them because it's not hard to see. But if I have disjoint, if I have the set, that is represented as product of disjoint subsets, then I have nothing else but product of this set. So on the picture, if I have no diagonal of some set here. So in this case, the factorial measure is just the product of corresponding to one-dimensional measures. But if the set lies on diagonal, so if I have rectangle here, and for simplicity we consider square of so I have equal sets here, the product of equal sets. I have nothing else but the factorial power that we discussed, just factorial power of the number, this one. And if I have here the third property says how we need to modify a little bit the how we can compute the second factorial measure for rectangular that cross the diagonal. So we just need to take usual product of one-dimensional measure address and subscribe the measure of diagonal of intersection of subsets. So this is some properties of factorial measures of a point process. And now I will define factorial moment measures. So if I take the expectation of a factorial measure, I will have the factorial moment measure. And now we will see that we can define the density of these factorial moment measures. But here a little bit some easy exercise to find a factorial moment measure for Poisson point process. I recall that on the previous lecture we considered such a process, and this process characterized by the property that it has independent Poisson values on the non-intersected intervals. So from this can be easily get that factorial measure is just the product of one-dimensional intensity measures. Okay, and now the next step in our consideration is define so-called endpoint functions. Sometimes in literature they are called as endpoint correlation functions or endpoint density functions and so on. But this is the analog of those functions that I defined on point process on Z. So okay, more specific, if the m factorial moment measure, this is absolutely continuous with respect to Lebesgue measure, then the density, which we will call Fm, is called the endpoint function of the point process mu. So this is just the definition. And the probabilistic interpretation of this K point function is almost the same as we saw in the case of for point process on Z. This is just the density of the following probability that we have that the point measure have a point in some fixed position x1, x2, and so on, xk. So this is just the density of such probability. Of course, for small intervals, such probabilities are equal to tends to 0. So we consider just its density here. And now it turns out that such functions define a point process. So we saw that it is true for a point process on Z, and under some condition it is true for arbitrary point process. This problem is an analog of problem of moments. So I will not just take I will not give here the precise statement, but in many cases these functions fk define the distribution of point process. And now I want to show that we can structure of this k point functions define some properties of interaction between particles. And here I want to come back to the first two examples that I considered on the previous lecture, and here just for reminder that we have that I considered an example of photons or of bosons and fermions, and we saw that these are two natural classes of particles that we obtain under assumptions that we consider indistinguishable particles in space. So we have two classes. One class is described by symmetric wave function, and the second with antisymmetric wave function. And it was proved by Adil Maki in 1975 that a system of bosons can be described only by so-called covariance of wave functions. So if I consider such covariance, then k-point functions is described as permanent of such matrix. So this is so-called permanent point processes, and from this, so what is the idea that we can just intuitively understand that if we have here symmetric wave function, we will have such symmetric k-point function of this system. And from this we can get some property of interacting between points in this system. So we will get so-called bunching effect for system of bosons. So indeed, if we have a general formula for k-point functions as permanent, we can get that the density to obtain a particle in a state x is equal to some value. And then for 2 points, so I just consider 2 points, then just from the definition of permanent of a matrix, I get the following formula, and we see that here we have plus, and from this follows that the probability to observe a particle in neighborhood of state x2 if we observe a particle in neighborhood of state x1 is bigger than probability to observe particle in state x2. So this means that if I see here x1, x2, and I know that I observe a particle here, then this means that with bigger probability I will find, or vice versa, I'm sorry, vice versa. So I observe a particle in state x1, and this means that I will observe with higher probability a particle here. So this means that 2 photons tends to aggregate. So I just write here the conclusion that a posteriori probability to detect a boson in a given state when another boson is has been detected is higher than a priori probability to detect a photon in that state. So just from obtaining the k-point function of a system, we can say something how particles interact in the space. The opposite picture we will see for fermions. So we saw that for the fermions we have antisymmetric wave function, and it was, oh, I'm sorry, I didn't correct determinants. And also by Adil Maki was shown that k-point functions is nothing else but determinant of the following matrices. And this will give the opposite property for the true fermions. So just from the definition of determinant, we will have here minus, and so the conditional probability now will be less than unconditional probability to find a fermion in some state state x2. So from this, we get the conclusion that a posteriori probability to detect fermion. So one of the example of fermion are electrons, and so this posteriori probability is smaller than a priori probability to detect fermion in that space. So from this, fermions tends to exclude each other. And this is the picture of a simulation of determinantal and fermanental and permanental point processes, and also we compare it to Poisson point processes. So here for Poisson point processes, I want to recall that we have independent number of particles for non-intersected subsets, but in the case of determinantal point processes, this is the case which describes bosons. So we can see that they just not come close to each others, and for permanental point processes we can see some clustering, so-called. So this is the main picture of such point processes. So we saw two very nice examples that came from quantum physics, and these examples show us that structure of k-point functions can say us a lot about properties, how particles interact between each other. And now I want to come back to point processes that corresponds to the ARRATIA flow. I recall that ARRATIA flow is a model that consists from a family of Brownian particles. So here that starts from each point of the real line, and they move independently up to their first meeting. So if they meet, then coalesce and move like one particles together. And we have such a picture from each point of the line. So we have such a nice picture here, and so. And to find some point process here, we fix a moment of the time t, and I consider the point processes that is defined as follows. So I just count the number of Brownian particles that came to set B. So on the previous lecture, we discussed that for a positive moment of time, we have finite number of particles in the bounded subset B. So we can discuss this point process. And a very nice structure of this point process was obtained by Tribe and Zaboronsky in 2011, and they showed that now k-point function is another combinatorial structure which is a so-called Pfaffian of a matrix. Here maybe I will recall what is Pfaffian, and then we come back to this picture. So here the Pfaffian is defined for a matrix of the size 2n by 2n for skew symmetric matrices, and this is a polynomial of degree n, and and the formula for it is the following: that Pfaffian to the square is determinant of a matrix A, but since we know that k point functions are non-negative, we can write this just a square root of determinant of A. So now we can see that this is now not the case of determinant point processes that they describe fermions, and it is not the case for bosons. So we have something else in this picture. The formula for k point processes has such structure. So now here I want to say that
excuse me, could you please show us example, for example, for matrix 2 times 2?
2 times 2. So here, of course, so the main what we will have skew symmetric matrix. So in this case, we will have matrix A of the following form, and this is just a square. So Pfaffian of such matrix just A.
Thank you.
So yes, it's not so obvious. So why we will have here a polynomial of degree n in terms of this numbers.
So we will consider only the formula like square root of determinant A. Yes. So we can forget about general definition of Pfaffian and remember that if we have skew symmetric, then it's just square root of determinant.
Yes, right? Yes. And of course, it is also important that we know that this one is non-negative. So because it's from this definition, you do not know what is sign you have here, but if you know that we have non-negative, we have plus here. Yes. So we will have just yes. In this case, we will have skew symmetric matrix here, and yes, we can just find the determinant of it and take square root. And also, we can write the same as I did for 2 points in order to see how they interact. And here I just write down the. I'm sorry. Here I forgot why, but maybe it's not important. So we have the following formula, and from it we also can see that we see that the probability to get to observe two particles and just in position x1, x2 is less than observe just a particle by itself, because we have here negative summand. So I just plot this big function and we see that it is negative. So this is how we can get some properties for particles using the k-point densities. And another questions that we can consider when we investigate point processes is its properties with respect to space shifting. So this is the question about its ergodicity. So and to start investigate this question, we should mention that in the definition of ARRATIA flow, two trajectory of Brownian motion is such that their joint quadratic variance depends just on the distance between 2 points here. So this leads us to the idea that the distribution does not change if we will shift the system of particles on with respect to space. So this is the picture. And also what is important here, that particles that we observe on a large distance are weakly dependent. So it's easy to understand, because if I consider two Brownian motions that starts on a large distance up to some point time t, with high probability they do not meet one another. So this leads to a very nice weak dependence. Why? So how we can characterize weak dependence? We can characterize it using so-called mixing coefficient that says us how much they dependent. So if they are independent, then this probability is 0. But if they dependent a little bit, this difference is small. And here this sets A and B are considered on some distance h. So here distance h, and I considered some sets A and B. Okay, this is B, this is A. And if we will have a good mixing coefficient, this will allow us to get some limit theorems for weakly dependent random variables. And indeed, we have such a good upper bound for alpha mixing coefficient. So we can see here that with respect to h, it converges to 0 extremely fast. And from this, we have I'm sorry, this is not 70. Law of large numbers. For number of clusters on the interval 0u. So this means that I observe how much points I have on the large interval 0u, and I just normalize it with the length of the interval u. So this statement...
And is this convergence almost sure?
Yes. So this statement can be easily obtained if I represent the number of particles in the interval 0u as sum of number of particles in k plus 1. Okay, this k from 0 to u minus 1. Okay, assume that u is natural number, and these random variables are dependent, but they are weakly dependent, and they have same distribution, because we discussed that distribution of a ARRATIA flow does not depend on shift. So if I shift unit interval, then I will have the same distribution. So this is just a law of large number for weakly dependent random variables, and what we need to check just that they have such first moment. And in the same way, it is possible to calculate the second moment of these random variables, and we can find the central limit theorem for number of clusters, and the idea is the same. So we just represent the number of points on a large interval as a sum of number of particles on unit intervals, and they are these summands have same distribution, but they weakly dependent. And here we just apply known result for weakly dependent random variables, and what we need just to find the variance, the limit variance, and this can be obtained from the formula for k-point function that was obtained by Tripe and Zaboronsky. So this is all for my lectures, and just to summarize, the main idea of my lectures that I wanted to show that a system of particles is can be investigated using a theory of point processes, and we saw that we can characterize them by so-called k-point functions, and we saw some classes of these functions that show us some properties of interactions between two particles. So this is all, and thank you for your attention.
Katerina, thank you for interesting lecture. And this was a second lecture of Katerina devoted to point processes. So maybe somebody have comments or questions, please. Katerina, maybe do you know not every point process, even stationary point process, are either Pfaffian or determinant?
No, I do not know this. So you just ask about all possible classes of these k-point functions. So do we have determinant, permanent, or Pfaffian structure of it?
You see, actually, the question is following. Because I think that maybe artificially we can construct a point process which is not Pfaffian, not determinant. But the question is following: we have natural coalescing flows, like Harris flows, for example, or the same ARRATIA flow with drift, or something else. Then, do you know some examples where we have not this Pfaffian structure, for example?
For coalescing, unfortunately, no. I don't know such examples. Maybe
it can be interesting to understand the relationship between coalescing phenomena, coalescing how to say, mechanism, and the structure of related point process.
Yes, I see. Yes, it's interesting.
Okay, I have one question. You have these correlation functions f1, f2, and so on. And what are some simple, maybe sufficient conditions that ensure existence of point process, like Kolmogorov theorem on existence of random process?
So if I have such functions, you see, existence of point processes we can get from condition of this factorial measures that we discussed. So if I have some upper bound on each some with respect to k, unfortunately I don't remember some upper bound that depends on k. Then we have there exists a point process with such k. Yes, such moments. So from this, maybe we can get some assumptions on or some properties for functions f, because using them we can get their these moments. This just mentioned. But just for arbitrary function. So if I have a family just in some space, or unfortunately I can't say for sure here for some conditions, just in terms of factorial measures we can get something. This is what I know.
Okay, maybe if there are no other questions, then we have to thank our speaker today. And the next lecture, Katerina, do you remember who will be the next speaker?
I can find this. Just a moment. I will. So you scheduler, and we will see that our next speaker is Vovchansky. On the next speaker.
Okay. So Thanks everybody and see you next week. Bye.
Yeah,
Thank you.
Bye-bye.
Goodbye.
Thank you. Bye.
Thank you.
Катерина,
Yes. Yes.
а вот последнее центральное предельное теореме, там скорость известна вам или это чисто так?
Скорость тоже, там можно получить аналог неравенства Бария-Сена. Там условия выполняются, то есть я, к сожалению, сейчас не помню, но скорость найти можно. Она, ну, опять же, я применяла известную теорему для слабозависимых.
Там у вас ваш процесс приводится к сумме слабозависимых случайных?
Да, вот мы можем рассматривать, значит, количество частиц на большом интервале как сумму частиц на единичных. И на далеких интервалах
они слабозависимы.
Да, они слабозависимы, и выписывается коэффициент перемешивания. Он очень быстро бывает к нулю, и поэтому можно получать и неравенство Бария-Сена на скорость.
Спасибо большое.
Да.
Очень интересный доклад. Всего хорошего, спасибо. Еще раз.
Спасибо вам тоже.
Успехов.
Спасибо большое.
До свидания.
До свидания.